Okay, we are recording now and we will get rolling. So, good morning once again. Today's session is about system level testing. This was somewhat by popular demand. I honestly don't recall who, but I think a couple different people requested a session on this, and I had material from some different presentations that I pulled together. So here we are. So we're going to start with GEVS section 2525. This is a new section in the most recent release well, I think I prepared the updates in 2018. It was released, I should know this, but I think around 2020 or 2021. But there had been no system level guidance provided in previous versions. So it was time that we put something in there. So MIL Standard 461 addresses component or subsystem level testing only. And so in MIL Standard 461E's, component or unit level refers to an individual electronics box, and I should put and associated cabling, because I've hammered that point home in previous presentation. So component unit level tends to be used kind of interchangeably. I believe that the MIL Standard talks about component. I realize that for a lot of designers, component means something like a resistor or a capacitor or an IC, but that's the nomenclature used in the MIL Standard. So just passing that along. So system level refers to just basically any higher level of integration, anything higher than the component or unit level. So typically instrument payload level or spacecraft and observatory level. So we're going to talk about each of those, and I'll give some examples of each of those as well. So there is some system level guidance provided in MIL Standard 464, and I really will emphasize guidance. It's not really, it's not at all along the lines of MIL Standard 461, where which is very explicit about at least the test methods. You do CS 101 this way, and then there are default limits that you can tailor and so forth. But MIL Standard 464 is more general. There are a couple of specific things that I will point out that we do draw from, but just because it has that MIL Standard prefix and even the 4.6 prefix, just don't assume that it's much of a similar document to MIL Standard 461. It's not really. But MIL Standard 461 nomenclature is not appropriate to use at system level. So any of the CE 101, CS 101, any of that nomenclature that we use for component level testing, do not use that for system level tests. It just creates confusion, and we want to minimize that. So while some test methods are similar, and the goals really are always the same, right? You're trying to ensure compatibility. So the goals really are identical, at least at a high level. And the test methods are similar, but they are different and they must be designated differently. Okay, it seems like a small point, but it's not. Like when you say when you say you're doing RE, I'll give you a specific example. Say you're doing RE 102. At component level, that means some very specific things, including a 1 meter distance from the test antenna from your test article. And when you're doing RE at system level, you're not really bound to that. You want to put, I'll get to this here in a bit, that you want to put the test antenna in a location that's representative of the antenna that you're trying to protect, which is not necessarily going to be at a 1 meter distance. So just if you say RE 102, that can get interpreted in some very specific ways at system level. It may not be what you want. So just avoid that nomenclature altogether and avoid that risk of confusion. So at minimum, the following tests at system level are recommended: power quality, aggregate radiated emissions electric field. That's what we call it. We just call it RE for short. Aggregate radiated susceptibility to electric field. And then system self-compatibility, which is subdivided into RF self-compatibility and then compatibility between non-RF components. So we'll get into the specifics of all these different things as we go along here. So starting with power quality, excuse me one moment. Okay. So we'll start with power bus aggregate voltage ripple in the time domain. And the recommended or default limit is 1 volt peak to peak, or plus and minus 500 millivolts from nominal in the time domain with 20 megahertz bandwidth. This seems to inspire a lot of confusion. I mean, those two ways of stating it are identical: 1 volt peak to peak, or plus and minus 500 millivolt from nominal. But that's why I write it both ways so that it's explicit. Because I mean, 1 volt peak to peak should be pretty clear, but sometimes that gets interpreted as, well, does that, or I get asked, is that 1 volt peak to peak, or is it plus and minus 1 volt? And my answer is, well, no, that would be 2 volts peak to peak. So when you're specifying this, I mean, the way I look at it is that it's pretty hard to over specify. Just specify it both ways so that people know exactly what you're talking about, and you don't have to keep asking the question or answering the question. And then we'll also look at turn on and turn off transients, and our benchmark will be we'll compare the measured transients to the CS06 pulse that was applied at unit level, if your program did indeed apply it. And so this is the CS06 pulse we talked about in one of the recent sessions. And it has a 10 microsecond pulse width, the default pulse in the standard anyway, 10 microsecond pulse width. And then we generally apply positive and negative going transients equal in magnitude to the bus potential. Now that's really a GEVS tailoring. That's not really in the mill. That's not in the mill standard. The mill standard, I think, default applies. We walked through that. I think it applies like 200 volts or something like that. So this is kind of standard for how we've done it at Goddard for decades. But it's something that, and this came from the previous version of GEVS that before I had anything to do with it. So just that's not how it's default how it's specified in the mill standard, for what it's worth. So here's just a representative diagram for how you would look at power quality at instrument or payload level. So you would have your power supply in your spacecraft simulator, or just an EGSE power supply, and you would want to go through a LISN that represents the spacecraft source impedance, because you're ultimately measuring voltage, which is going to be dependent on, or it's going to depend very directly on that LISN impedance, or just on the spacecraft source impedance. Mostly what we're looking at is potential, but if you're going to instrument this stuff, it doesn't hurt to look at current as well. So, and then you connect that up to the power feed of your instrument or payload. There's LISN. So obviously one of my biggest set of case studies comes from JWST. So we'll start with the JWST ISIM, the Integrated Science Instrument Module, the science payload. We ran this test almost 10 years ago, August 2015. That's our motley crew in the large RFI chamber here at Goddard, and that is the ISIM behind us. And I'll talk a bit about different tests we performed on it. In other presentations, I swear I didn't do this on purpose, but if you look at the movie poster for the Magnificent Seven, it looks pretty much like this, well, except that the guys are on horseback, and wearing cowboy hats instead of, clean room garb. And I'm in basically the same position in the center as Yul Brynner. So I swear I didn't do that on purpose, but I love that coincidence. And I have actually put that in some other presentations, but taken that Magnificent Seven poster and put it right next to this. So can't resist having a little bit of fun with that. So, but moving right along, we did specify and have a custom LISN built. You can actually kind of make out the Solar Electronics label here. So Solar made this Lizen for us, so you can see the impedance specification from the spacecraft vendor is the red dashed line, and then the measured Lizen impedance is the blue line. Once you get up above a couple megahertz, and I've mentioned this before, it's kind of non-trivial to get that to get the impedance right. And we've tried building an in-house Lizen, and I think we were actually able to get up to about 10 megahertz, but just the parasitic capacitance between your inductor windings and stuff like that. There are just a lot of ways that make it difficult to get the desired impedance as you go up in frequency. So I'm sure they were doing a bit of tuning and tweaking to get things to get pretty close to the line here. But anyway, the Lizen impedance matches the specified impedance pretty well, and this is what we went with. So the general power quality test setup is applied to this test campaign. This is the power supply in the EGSD rack in the spacecraft simulator, and then we ran it through a Lizen. I have a photograph of it on the next slide, and then we put our voltage and current probes, at the Lizen outputs. There is on a little platform on the rack, and then it ran that power feed into the EPS simulator. It's basically a switch box. So I don't think there was any filtering in there. I mean, I think it was just taking the power supply feed and then running it through these relays to the different power feeds. So there's a photograph of it. So this is the spacecraft simulator. I believe the spacecraft simulator was actually this dual rack, this whole thing here. But we were able to run the power supply feed out to the front, to the Lizen input, and then just go from the Lizen output back inside. Obviously, that's a live power feed, so you got to treat it accordingly. We put Kapton tape over everything so we didn't have any exposed metal. But yeah, there's your 28 volt in, 28 volt out, current voltage probes, and away we went. So here I'll just talk about timing for a little bit. Obviously, the first thing we did, first thing I certainly recommend you do are inrush transients. You just do that in the course of turning boxes on. Now, ISOM had a lot of boxes. I think it was 13. I don't think we specifically picked that unlucky number, but that's where it landed. But I think there were 13 boxes to power on. So like once you instrument all this, once you make the decision that you're going to do all of this, that you're going to instrument this and set up to measure voltage ripple, which is really kind of the main thing. Like you actually have a requirement to verify with this. Then, I said, well, I want to measure those inrush transients. We're already instrumented to do it. We have to turn boxes on. There is no additional time required to do it. So that's just like the order of operations. But I'm just presenting these data first, but we'll get to inrush here in just a moment. But these results were kind of wonderfully bland, just a bunch of white noise. This is with everything powered up and operating kind of in a normal configuration. We did run in a few different frequency ranges, and we used a scope that could take an FFT, so you can do that if you want. That wasn't really required, but it was just something we did with the capabilities we had to get some idea of some of the frequency content. But just in the time domain, there was nothing really stood out. It was just a bunch of fuzz, a bunch of white noise. The worst case that we saw was 144 millivolts peak to peak. That was well below the 1 volt peak to peak limit, so passed with flying colors. So great, this is exactly what we want. So then looking at turn on transients, there were a bunch of them, like I said, 13 boxes and a bunch of heaters and things like that. And there was a whole, the data review after the test, all that stuff's in that presentation, was in the test report. But I'm just going to show you some representative ones here that are the most interesting. So, during instrument level testing, and this is the fine guidance sensor guider 1 channel, they were all pretty similar. I mean, the front end of all three portions of channels or sub-instruments of the FGS instrument, the front end was pretty much all the same. So all of these turn-on transients look pretty much the same. So there was this relay chatter that was a known GSE artifact. So we weren't really looking at that so much as our benchmark. This part of the transient, this is what we know is the true character of the box turning on, or of the power converter coming online. So that's the true transient of interest. Why it specifically looks like that, I don't really know. That's beyond the scope of what I'm going to talk about. But this is our benchmark. This is what the data we already had going into the ISOM test. And so the main thing is I'm looking for, is it in family? Do we see the same basic characteristic? Well, it's pretty unmistakable that yes, we do. That current profile, I mean, you can't really get a better match than that. I mean, just looking at it qualitatively, but that was more or less all I was doing. I mean, yes, looking at magnitude too, and then we're looking for the voltage drop for in the peak part of the current transient was only about half a volt. So nowhere near that CS06 transient of, minus 28 volts. So that's very benign, and that's good. That's what we want. Right. So the turn on transients are pretty benign. We want to be aware that when you're turning these boxes on, you might get a half a volt of drop on the power line, but that's not terribly likely to have any adverse effects on the bus. And then for turn off transients, the worst case, I had actually remembered that we never got the scope to trigger, but we did get it to trigger on this one. So, and this was another added bonus. We had to turn the boxes off anyway, and we got what we got. I mean, we weren't going to go back and say, oh, do it again. Turn the box on and turn it off again. It would have been great to expand around this to get more time resolution, but so just in case any of you are asking, oh, why don't you have better time resolution on that? That was the reason. We were getting this for free, and we got our one shot at it. But this just shows that it went up above and below, the nominal by about a volt. So that, again, that's quite benign. Again, when you're applying CS06, you're applying bus potential, plus 30 volts and minus 30 volts. So I call that benign. And then pretty much all of the other units, we didn't really get the scope to trigger at all. Or we were triggering on current, I believe, was how we got a trigger in the first place. So we knew the current was going to drop. So we would trigger on the current, but there's no measurable transient resulting from that, and that was typical. So transients are not a big concern. Was the conclusion we came to there. Anybody have any questions so far, or just give me an I'm okay that you're still there?
Here.
Excellent. The ulterior motive is it gave me a second to take a sip of coffee. All right. So now still looking at power quality, but now moving over to spacecraft observatory level. Well, so here you don't need a LISN. You're looking directly at the spacecraft power subsystem. So you're looking at the spacecraft source impedance directly. So you don't need a simulator network for it. Now this is all depends on having a test point that is available. If you have some place where you can actually connect probes and access this point, then great. And to state the obvious, you are connecting to a live power bus. Well, ideally you should be connecting when it's not live, when it's powered off, but you have probes running to the power feed, the main power bus of the spacecraft, which is going to be live. So you need to take proper precautions, make sure everything is well insulated and everything else, and secure those leads down so that people don't trip over them or any of that stuff. So anyway, you're hooking up to the spacecraft in the flight configuration, so you don't need a LISN, you just need a place to connect your probes. So here's our motley crew from the JWC spacecraft EMI test out at Northrop Grumman in the early part of 2017. Here's the power quality setup. I say that we did the spacecraft test in two stages. The conducted tests were this part, in February, March, and then the radiated tests we did about a month later. So they were two separate test campaigns. So don't get the impression that the test took a month and a half. Each one of these tests took days, but which is one of the major points I'm going to drive home. But so here's the setup where we took advantage of an opportunity when the panel with the PDU was still going to be open, and ideally you would want everything in the flight configuration and all buttoned up and everything, but with it all buttoned up, we'd be less likely to be able to connect our probes to anything. But as we were planning the test, or at least expressing a desire to do this, all of this is planned, well in advance, by the way. This months, if not probably a year of planning went into each of these tests. But as we were just talking about how we would do this, when we saw we would have a window of opportunity before closing this panel, and we said, yeah, okay, it's not really ideal that the panel's not going to be closed up, but for a conducted test for power quality, probably okay. It's probably not a very significant compromise, and it was outweighed by how straightforward it was going to be to do this, right? We have an opportunity to do it, then let's take advantage of it and let's do it. So the point we wanted to access was very accessible. We could get our current probes right where we wanted them, and these are those gun type current probes with a large window, which was great. These are exactly what you want for this kind of test. We're making measurements in the time domain. A scope based current probe that is specifically tuned and it's designed and tuned and built to give you good time domain representations of your signals. That's what you want. It's a little more complex when you're using the donut type current probes, and you got to take into account the transfer impedance and all that sort of thing. So we had these gun type current probes, and there was a T adapter that was specifically made to give us access for our voltage probes. So I'm seeing a question. I thought it was from you, Mike Rosa. Go ahead and speak up, because I'm not really looking at the chat window.
Yeah, it's me. I was like, so did they design this testing to be capable of being done, or was it something that you looked at it and said, okay, here's what we can do given the spacecraft design as it is?
Well, I think this T adapter that's a simple thing that they just designed and built for the test. But I don't think anything else was specifically designed. I think these external cables, I think I can see over here, I think that this may be the B side of the PDU. But like a lot of boxes we build, these external cables function as the backplane. Excuse me. But they gave us access to the places where we would want to hook up our current probes. So I don't think they had to do anything special. I think that was already part of the design. Maybe they built an extender cable. I don't actually remember. But whatever they built, like this T adapter was very simple. It probably took a technician less than a day to build. Probably if they built an extension cable, that's probably about the same. So
just expecting that to do this kind of test on a lot of satellites, you'd have to have this as part of the initial design concepts of the spacecraft.
Well, we didn't really have that when in the initial design phase. I think it was just fortuitous that they had some of the stuff that was going to be accessible, and we had this opportunity to do this testing when the panel was still open.
Okay, thank you.
So yeah, you're giving us a little too much credit for thinking ahead many years in advance. I wish that were true, and I'm certainly encouraging people to think about it now for programs in the early phases. So, okay, moving right along. So we were instrumented with our voltage and current probes, and bus ripple was again very benign and boring. 300 some millivolts peak to peak, well under the 1 volt. And we took a bunch of plots, by the way, and we didn't just take this one plot and call it a day. We took several plots over some period of time. I don't remember, 20 or 30 minutes or something. And they all looked pretty much like this. This was the worst case. And so no real issues with bus ripple, and that's what you want. So for turn on transients, again, just you're instrumented anyway. It's the same instrumentation, voltage and current probes at the distribution point. So you just take these measurements when you're turning stuff on, and you get one shot at it. Maybe just maybe if you ask nicely in advance, you might be able to get a couple. I think maybe we did actually take a couple of shots with this. Like if the trigger was, because you got to get your trigger set up just right and have the time base set up the way you want it. And if you're not dealing with a unit, I mean, sometimes you do have a unit where like you really want to minimize power cycles. In which case you know up front you got one shot at it and you get what you get. But in the course of planning the test, and I think we probably did put wording in there, repeat as needed until the test team is satisfied that they've got the necessary data, something like that. Anyway, your criteria here is using that CSO6 pulse as a benchmark. For any transients that are less than 10 microseconds, the CSO6 pulse width, we want to be less than 30 volts. So that's pretty generous, at least for those shorter pulses. Because we know we've tested everything to that CSO6 transient. Okay. But for anything greater than 10 microseconds, we just said we don't want the bus potential to dip below 24 volts. Okay, so a delta V of less than 6 volts for a 30 volt bus potential, which was what we had. I think it was maybe a little higher, 30 point something, but this was what we. I mean, this is right from my charts on the data review from that test. So we just said, okay, we're looking for any transients that are longer than 10 microseconds. We want the delta V to be less than 6 volts. So the worst case measured turn on transient was from the contamination control electronics, the PT, which I think stood for pulse tube. There were two sets of contamination control, not contamination, cryocooler control electronics. There's the PT pulse tube, and then the JT, I think, was Johnson tube. The worst case was clearly the PT, but I'm showing them both for completeness. So the delta V was about half a volt for about 100 microseconds. So fairly long transient, certainly longer than 10 microseconds, but the bus dip was only about half a volt. And that was from a very sizable current. We knew from unit level testing that this was likely to be the worst case transient because the delta I was 30 amps, and that's what's on the next slide. So turn on transients, not a problem on the JWST power bus. And again, we took these plots for every unit that we turned on, and this was by far the worst case. Most of them were very benign. Now, for the current, there isn't really the main criteria here were that these two units submitted waiver requests because they measured these transients at unit level. And so we already had in the record that these were going to be very sizable transients. And so the criteria were that the peak current for the pulse tube would be less than 64 amps, and for the Johnson, I'm just going to call it JT, it would be less than 32 amps. Well, both of those were less than that. So what I take from this is that the actual source impedance on the spacecraft was different or a little bit lower than maybe what they used at their at unit level, or at unit level maybe they used the the capacitor network so that they got a worst case current, which is exactly what we want. But with a little bit of a, so I would say, I guess the actual source impedance of the spacecraft is probably a little bit higher in this frequency range, so that it's limiting the current a little bit. That's at least I hadn't really thought about it before, but that's my quick assessment of possibly why that's the case. But the real point here is that these currents are less than what we had already approved in this prior waiver request. So we were good to go. These current transients and the voltage transients from the previous page said, okay, this is not going to be a problem on the JWST power bus. So turn off transients. Again, we wanted the delta V to be less than 30 volts for any durations less than 10 microseconds per the CS06 characteristic. And we didn't want the bus potential to go above 40 volts. So a delta V of less than 10 volts, or dip below -2 volts for any transients less than 50 milliseconds. Okay, but we never got the scope to trigger a single time. Right, not once. So turn off transients are not a problem on the JWST power bus. So the JWST power bus includes about at least 5,000 microfarads at the distribution point inside the PDU. And this is very similar to a lot of our recent in-house designs that our power group here have implemented. That, you know, when you're bringing, let me go back to the picture. So just the distribution point, you know, I've generally pictorially represented as like a pair of copper bus bars somewhere in the spacecraft near the battery. That's not what we had here, and I think that's not very typical on a lot of recent missions, and that's certainly not what was done here. The power feeds to any given unit, the cables run back to the PDU to their respective connectors, and then the leads go to a point on a circuit board in the PDU and that's the distribution point. And there's about 5,000 microfarads of capacitance hung off of there. I'm sure it's multiple capacitors, a whole bank of capacitors, but it's many thousands of microfarads at that distribution point. And that large capacitance, of course, is going to absorb much of that energy from the transients, minimizing their impact. And in the case of the turn off transient, it basically gives you something you're just not even going to measure. It just snubs it all out, and it's not an issue at all. So had this been understood and characterized earlier in the program, such as, for instance, during the requirements definition phase, we would likely not have applied CS06. And we have applied this lesson learned to more recent programs, RST included, where that's an in-house program implementing the same architecture that I described with the big capacitor bank at the distribution point. And I believe the power group, characterized that system possibly on early breadboards or maybe heritage designs from other programs, and just showed, yeah, we're just not going to have an issue with transients on this power bus. So if you know that going in, then CS06 is not really a test that you need to perform. So I think save some time during unit level tests. I don't really like putting things in those terms necessarily, because choose my words carefully here, I guess. But then I'm retiring. Why do I need to care? But it's not so much about saving time. Because if you want to just save time, you're just like the Emperor and Amadeus. Too many tests, just don't do any of them, and that's obviously not the point. But it's making the most optimal and efficient use of your test time. So if something's not a concern, then don't run the test. So, I mean, that should be obvious, but that's also a statement I don't like to make. So I'll make it anyway. Just. It's about making efficient use of your test time. It's not just about saving time. So hope that's clear. So let's keep moving. Okay, that is now we're shifting gears. We're moving from power quality and conducted tests to radiated testing. So anybody have any questions? We'll pause here for just a moment. Any questions or thoughts before we shift gears?
Yeah, I was just thinking about what you said about, if you don't think you need to do the test, then don't do the test. I mean, I guess if you're, I guess you need someone who's really knowledgeable in this area to guide you there. Otherwise, you just, kind of blindly blanket, apply all the tests.
Well,
But yeah,
that's a good point. Is that Glenn?
yeah, it's me.
Hey, Glenn.
Yeah.
I just that's a good point. So I think it's worth. I just want to emphasize that it's not just that really shouldn't just be one person saying, yeah, CSO6, yeah, we're just not going to do that. I mean, it should be, done with proper discussion with the necessary people and stakeholders, and that you come to a consensus and a deliberate decision that that's the appropriate thing to do. That I didn't just make that decision unilaterally on RST. I spoke about that with our power group here, and I think it was that this very experience that I just related on JWST, where I never got the scope to trigger on a positive going transient for a turnoff, and the worst case negative going transient was a whopping half a volt from a 30 plus amp transient. I just and then when I learned that mainly from talking to Mike Burns and Brad Kercheval, or my neighbors here in Building 20, at least for the next month and a half, they said, yeah, we have a similar architecture that we've been using. We put thousands of microfarads there at the distribution point. And so I said, okay, then transients really aren't going to be a problem on that kind of bus. And they agreed. That's the nature of things when you put that much capacitance at the distribution point. So it was from a deliberate discussion, and it wasn't just like an off the cuff single discussion. It was a series of conversations with different stakeholders, and then agreeing, yep, this is the right thing to do. Let's get rid of CSO6. I think it was in there in an early draft of the requirements document, one that I inherited. And then as we were going over things and I was overhauling some of the requirements, okay, I guess kind of all of them. I made sure we got the appropriate people together and agreed, okay, yeah, we don't really need to apply CSO6. So we were able to delete it, but it was that kind of process. It wasn't just, this test is meaningless. I almost used the euphemism for bovine excrement, so I'm still trying to behave myself a little bit. But anyway, does that answer your question?
Yeah, it does. I mean, yeah, thank you. That insight.
Okay. Anybody else? Now we'll plunge into radiated. Okay, so aggregate radiated emissions electric field. In case I hadn't mentioned it before, it's not RE102. I guess I'm violating the prime directive, because the more I say not RE102, the more you might tend to actually use it, but please don't. RE102 is by definition a unit level test. The use of that nomenclature for tests at higher levels of integration has caused confusion and must be avoided. So at instrument and payload level, we'll have two sets of limits generally, on-orbit limits and launch limits. It's really only necessary to measure in the frequency bands occupied by intentional receivers on the platform and at the launch site. So those are the notches in the RE limit curve. Okay, and make our measurements with antenna locations are limited to locations that are representative of the relative locations of antennas on the platform and at the launch site that are being protected by the defined RE limits. So this is about being very deliberate and clear about what your victims are. Okay, this is one reason that system level tests can drag on for a while, is if you're not clearly defining your victims, and if there is a desire or tendency to just say, well, we've got to repeat the entire frequency range at system level and do our scans from DC to daylight. There's no reason to do that. Your specific victims are the platform receivers and the launch vehicle receivers. That's what you're trying to protect. So that's the frequency range and the antenna locations that you want for this level of testing. And at spacecraft and observatory level, you're only concerned about the launch limits, right? You address the there's a point of spirited discussion here, but at least my position is that you address the platform, the spacecraft receiving systems are addressed through self-compatibility, at least generally speaking. And I'm not in any way talking to Mike Rosa here. Are you still listening, Mike?
Yes. Yes.
Your pause made me think, oh, I pissed him off and he's hung up. Anyway, so this is the general philosophy. And then, of course, every platform is special, and you have your discussions about what is necessary on any given platform. But this is my general assessment of a going-in position, right? But your main concern at spacecraft or observatory level are your launch limits and your launch vehicle receivers. So you only need to measure in frequency bands occupied by the intentional receivers at the launch site or on the launch vehicle. So those are your notches in the RE limit curve. And again, antenna locations that are representative of locations of the antennas that you're protecting. Okay, so for susceptibility, it's a similar story. It's not RS-103. That is a unit level test. Don't apply that at system level. So at instrument and payload level, again, you're looking at both on orbit and launch limits. Now, for instruments and payloads, they're generally off at launch. So the launch limits are really survived without damage only, and that should be retired by analysis, which you should have already done by the time you got to this point. So if you've already done that, then you probably don't even need to run an RS test at launch levels. Okay, you should have already retired that risk by analysis. So anyway, only measure in frequency bands occupied by intentional transmitters on the platform at the launch site. So those are your tent poles in the RS limit curve. Got a typo here. Closed parentheses that doesn't belong there. And a mutant extra space there. So, and then a similar thing, measurement antenna locations limited to locations that are representative of the relative locations of transmit antennas on the platform and at the launch site. Now that's much easier to do with transmit antennas on the platform and on the launch vehicle. Launch site is a little bit of a different beast because you don't really know where those transmitters are going to be. But at least, for your platform antennas on the spacecraft, those you should know by the time you get to this point. And I'll point out that with RE testing, the scans are generally pretty quick, even with the old frequency swept receivers. If you've got a narrow, well-defined receiver notch, those sweeps are generally pretty quick. So you're in a little better position with radiated emissions if you're in any doubt about an antenna position. Do you need 4? Do you need 5? It's not going to make that much of a difference in time if you just go to 5, right? It just if you're already doing 4, another 5th one is if you're looking at a 6-hour day versus a 7-hour day, in the grand scheme of things, that's a drop in the bucket. So with RE, if you're in any doubt, throw in the extra antenna position. RS is much more time consuming, and you want to be much more deliberate about your antenna positions and just make sure that each one is truly value added. So at spacecraft and observatory level, again, for the same reason, you're really only concerned about launch limits. You're concerned about your compatibility with the launch environment, so the launch vehicle and the launch site. Again, only measured in frequency bands occupied by intentional transmitters. Those are your tent poles in the RS limit curve. And then again, measurement locations that are representative of the relative locations of the transmitting antennas on the launch vehicle and at the launch site. And then same statement applies there. You should know at least generally where they are in the launch site at the launch vehicle with respect to your equipment. The launch site may be a little harder to pin down. So going back to our case study here of JWST, so on the fully integrated platform, you see the ISOM. I believe I put these charts together for the ISOM level test, but they applied for spacecraft as well. So this is the ISOM structure here, and so the antennas on the spacecraft are in these three locations here. So this is for the on orbit level testing. So the spacecraft level receivers are the ones in question for RE and RS for that matter, because we have our high gain antenna here that's transmit only. And then in the launch configuration, the launch vehicle antennas are at least you got to look at how your launch vehicle provider specifies this. Here the JWST was on an Ariane 5, so the Ariane 5 user's guide specified with those RE limits that they were to be measured 675 meters, 675 centimeters. No, excuse me, 67.5 centimeters. Let me just read what's on here. 0.675 meters below the spacecraft interface plane. Okay, a well-defined document should be very explicit where they want you to measure those. So where the specific antennas are, all right, we tried to get some idea of like where they were kind of around the circumference, but that's where they specified that to take the measurement. So that's where we put our measurement antennas at spacecraft level anyway. So so here is the JWST RE limit. And again, we have two sets of limits. The launch is the orange curve, and the operational on-orbit operational is the blue curve. So you have our spacecraft S-band receiver notch. That's kind of the big one in question. We did have to test that at ISOM level, not at spacecraft level. And then the launch curve is clearly much less stringent, so there wasn't really any additional testing we had to do for the main part of the curve. But the launch vehicle command destruct receiver notch does come just a little bit below the default level here, so we did run an additional test for that. So and so those were the two main limits we looked at here at ISOM level. And this is maybe showing the age of these curves a little bit. I think some launch vehicle providers are not using the command destruct receiver. I mean, some maybe still are, but some are not, and have an onboard the guidance and navigation control system senses if the rocket's going off course, and it initiates a self-destruct sequence. I don't know that I like that any better. It doesn't really give me any more of a warm fuzzy than having a human operator on the ground send that command. But that's a different conversation. So anyway, and I'll point. I've probably pointed this out before, but I know when I first heard about these command destruct receiver notches, I interpreted them as, gee, if you emit anything in that receiver notch, if you're generating any incidental emissions in that receiver notch, you could blow up the rocket. I mean, it's like I said, I had that initial interpretation. It's very understandable that you might think that, but maybe you think that if just any spurious emission from any piece of equipment in that receiver notch could blow up the rocket, you would want to have a more extensive discussion with your launch vehicle provider about their command receipt and interpretation protocol. That would be a pretty bad design if a single little pulse could blow up the rocket. So that's not the issue. The issue is you could jam that receiver interface so that it can't receive that signal when you need it. And that's also really bad. Either way, the rocket blows up when you don't want it to, but it's for a different reason. Anyway, just pointing that out. Okay, so antenna positions for the S-band notch. As I mentioned here, the for RE, the scans are pretty quick, especially I think, yeah, we did have I think we had an ESW receiver by this point. No, I don't think so. I don't think we had the ESW receiver, the fast Fourier transform receiver yet. But anyway, we used 5 antenna positions here just to get full coverage because the scans were not very extensive. We used a small double ridge guide horn. You can see it in these different locations. All the scans were pretty similar. We didn't see anything sticking up above the noise floor or the general background. Well in compliance, a good 10 dB below the limit. So all good. Everything compliant with the S-band notch. Now, when we tested for the command instruct notch, full disclosure, we did actually do wide band scans on ISOM for additional engineering data, but the receiver notches were the most important thing we were looking at. So here we did a full scan from 200 megahertz to 1 gigahertz. The measurement bandwidth, the default measurement bandwidth of 100 kilohertz was the specified bandwidth to use in this band instruct receiver notch. So we didn't have to, we didn't have to change bandwidth. There's the 100 kilohertz right there. So it was all just part of the same scan. So we're fully compliant in the launch vehicle command instruct notch, no problem. There was this 319 megahertz peak that was just showing up throughout all of the RE data. The URSU was the only box powered on in the launch configuration, by the way. So we were in the launch configuration. The only ISOM component on at launch is the URSU, and that was it. That was all we had powered on. And so we shut everything up, sorry, getting ahead of myself. We went to the B side. Things looked pretty much the same. It was still compliant. We still had the annoying 319 megahertz peak. Well, when we turned everything off, it was still there. So it was not coming from ISOM. And we did eventually track it down to something in the lab. I think it was a light or something. Rob, are you on? Rob Hool? Okay. Well, I think Rob was like literally crawling in the crawl space above the large RFI chamber, and there was some I think some part of the lighting system that was generating this that we sorted out a few days after we finished the test. It was clearly not an issue outside the receiver notch. So at this point we just said it's below the limit. It's clearly not coming from the equipment under test. We're going to move on, and we sorted it out after the fact. Anyway, complied with the RE limits, and all was well. So for radius susceptibility, we used conical log spiral antennas. John Lishtig, are you on? Yeah,
John's out of the test site.
Okay. It's always fun when I mention conical log spirals when John's on the line, but John really does not like these things. They're a mixed blessing. You just got to be careful when you use them, but they serve a really good purpose here. They have a very large beam width, 60 degrees over the frequency range of interest. There are 2 different ones, by the way, so low frequency and high frequency, but both of them had about a 60-degree beam width, and they're circularly polarized, we talked about in previous sessions. So they give you both horizontal and vertical polarization simultaneously. So you just, with a strategically placed antenna, you can get full coverage in one position, one polarization. So one sweep, right? So it's additional time saving, or again, more efficient use of test time. And so we determined that if we move the antenna back, because again, with RS-103, you're not tied to excuse me, I'm violating the prime directive. This was not RS-103. But with RS testing, you can move the antenna back to whatever distance you need to get coverage, as long as you've got the amplifier power to give you the field you want. And so we moved it to 2 meters back from the front face of the ICE electronics compartment, the IEC, and that gave us this full coverage of that whole area of interest, that whole cavity, and that's within the 3 dB beam width of the antenna. So we were able to establish the low on-orbit levels within the power limits of the antenna. So quick war story is, I believe it was the higher frequency version, so the smaller antenna above a gigahertz. I think we tried to use it for the launch limits of 20 volts per meter, and turns out that used, if memory serves, I think the antenna is limited to 50 watts. And had we done the calculation beforehand, we would have seen that we needed a bit more than 50 watts. I don't think it was a lot. It was maybe 55 or 60 watts or something. You know, it wasn't like we were putting hundreds of watts through it, but we needed a bit more than 50 watts to get 20 volts per meter. And the antenna didn't like that. It got a nice brown tip, and it was hanging in the EMI lab's wall of shame for a while. But for the lower on-orbit levels, and I'll talk about those in a couple of slides, the maximum level is 6.3 volts per meter. It did just fine. So you can cover the entire IEC cavity with a single antenna position and polarization. So one sweep for each antenna, for each frequency range. So this made for a very efficient test. You know, we were able to basically complete RS in 1 day. And the desired field is established at the rear edge of the IEC. So I got some pictures here on, okay, it's slide after next. My apologies. But here is the IEC cavity, as it were. It was covered in this, you know, it was bagged for contamination control. But the actual rear face of the IEC is recessed here, so we couldn't get our field probes all the way back to be lined up with the front face of the IEC. We had to put them lined up with the front face of the structure here. And again, it was unfortunate that this was a metal structure that almost certainly affected things somewhat, but you know, that's what the ISIM was mounted to, and we had to deal with it. Believe you can see the field probes here, but I got a better view on the next page. So we put the field probes down here lined up with the front face of the mounting structure, and the IEC was recessed a bit. So we pre-calibrated the field to what the equivalent field would be at this location, a bit closer to the antenna, whatever it was, you know, 1.5 meters, 1.7 meters, whatever it was, I don't remember. But we did the calculation of, you know, if we want 2 volts per meter at the IEC face, then we needed something just a bit higher here, and so that's what we pre-calibrated to. So the primary figure of merit for the susceptibility was the performance of the detector subsystems, right? You know, this was the instrument payload, so this was the science data, the entire raison d'etre of the mission. So we had 18 detector channels amongst the 4 instruments. So the processing turnaround time, and again, this is all the stuff that we talked about in the months and months of planning for the test. How are we gonna, what is it going to take to process all 18 of these detector channels? And the prognosis, which was pretty accurate. I mean, the teams that do this processing do it all the time and have a good handle on this. They say, yeah, it's going to take about 40 minutes, give or take, you know, 45 minutes to process all 18 of those channels to get some kind of assessment of, you know, do we have a susceptibility or not? And that's a very inefficient and undesirable wait time. You don't want to run, at least I don't want to run a sweep and then just wait for 40 minutes before I decide what to do next. Okay, so so what we did was we just queued up the scans. And this is one of the nice things about another big fridge benefit of using a pre-calibrated field. And we pre-calibrated with the ISOM off. And we pre-calibrated to the full level of, oops, great, more typos on these slides than I care to admit. But 6.3 volts per meter was the full level, and that's worth a little sidebar as well. That the actual requirement was 2 volts per meter, but all these detectors are going to be operating at cryogenic temperatures on orbit, below 40 Kelvin, I think around 37 Kelvin. And so that's really the requirement, is to operate and spec in the on-orbit configuration, which means cold, at a level of 2, with an applied level of 2 volts per meter. Well, we were not going to be able to run this test with cold detectors. They were going to be run warm. Again, going over all of this stuff months in advance of the test. Looking at the logistics, okay, we're going to be testing with warm detectors. How do we evaluate susceptibility? Well, a lot of the early answers were, well, you can't. But the more we probed into it, the more, the detector teams said, no, you can. We can put and I'm probably going to get some of the specifics wrong, but basically they could put the detectors in this mode where they could read I think a reset pixel or something like that. You're not really reading out the array. You're looking at kind of the output amplifier, and it's biased in such a way to essentially short out the detector's contribution, and you're at least getting enough of a measure of the susceptibility of most of the detector element and the downstream electronics. And what you're looking for is some perturbation from nominal performance, without an applied external field. So you have some baseline performance. They would run FFTs and do statistics on the data. Then you apply the field, and you're looking for significant differences. And we did some characterization tests to compare. If we apply an equivalent field of 2 volts per meter, what's the equivalent at cryogenic temperatures? We had a detector operating in a Dewar, and we actually used CS114 to do this. But with an equivalent level of 2 volts per meter, what level do we have to apply at room temperature to get the same level of interference? And it was about 10 dB. So about a factor of, well, the square root of 10, 3.16. Well, 3.16 times 2 volts per meter, that's 6.3. Right, 6.32 if you're counting decimal places, but that's where this 6.3 volts per meter comes from, is the equivalent level to be applied at room temperature. I caught a lot of hell for this, by the way. Project wasn't real happy when I said, no, I want to test to a level that's higher than the requirement. And I had to go through a lot of rigmarole. I shouldn't say rigmarole, but just I stuck my neck out online saying, we are not doing the test properly if we test at 2 volts per meter with warm detectors. It will be an under test, and it will be a waste of time. And but I fell on my sword many times over this, and eventually it was like, yep, this is the right thing to do, and that's what we did. So we pre-calibrated to the full level of 6.3 volts per meter. And then the levels were just played back in a pipeline fashion for the official RS scans with ISOM powered on. So we applied the full level, and then while the team was taking their 40 minutes to process the data to determine do we have a susceptibility or not, we'd go to the next level where we'd go 6 dB down from the full level, and then go 10 dB down if necessary. By that point, they generally had the they generally had the results from the first scan. And if they didn't see any susceptibilities from the first scan, by the time we were done with the second, then, okay, there was no reason to go to the 2 volt per meter. And emphasize that 2 volts per meter is still 10 dB down from the full level. It just happened to be the level that we decided to go to being 10 dB down from the full level. But you know, if we didn't see any susceptibility from the full level, then there was no reason to go to that third sweep. So anyway, but with queuing up the scans like this, we're able to just keep things moving, and in the long run, it was much more efficient than just waiting for a go no go decision before proceeding. And we've applied this on a number of other test campaigns. I believe we've done this on some RST tests, and I highly recommend that you do this. If you're this is one of the questions I always ask as we're planning the test. What is your turnaround time for evaluating whether you have a susceptibility or not? Because if it's something upwards of 20, 30, 40 minutes, then you need to consider doing something like this. If you get more or less an instantaneous indication or within a few minutes, then you don't really need to do this. You run the sweep, you wait the few minutes until you get the decision from the data evaluation team, and then you move on. Okay, because you need to either move on to the next sweep or you're repeating part of the sweep you just did. Okay. Again, the log spiral antenna was sufficient for these low levels. And we completed RS in 1 day after an initial setback. And so there's another war story. No, this isn't the one about the burnt antenna. I already told that one. This is actually a different one. We had just taken receipt of a couple of new signal generators not too long before this test started. They're very nice signal generators, Roden Schwartz signal generators. We still use them in the lab. They're great workhorse signal generators. But we got them, I don't know, a month before the test, and the initial decision was, no, we're not going to use these for the ISIM test. You know, we want to make sure we check them out, fully understand them, and all that stuff. We're going to go with the tried and true, which is the right approach, right? That's generally the recommended approach. Is you go with the stuff that you know works, you know, especially for, you know, an important high profile test like this. Well, the temptation was too strong. We're like, oh, we got to use our new toys for the ISIM test. And no, I mean, we didn't damage anything or anything else, but it was what the long and short of it was that we ran about a day and a half worth of RS test without actually modulating the test signal. If you recall from a previous session, if I'd have thought about it, I could have had those charts ready. But for pretty much the entire range of the RS frequency range, the sampling rate for these detectors was 100 kilohertz. Yeah, 10 microseconds pixel period, so 100 kilohertz. So everything for these tests was above that range. So you're well above Nyquist, whatever. You're significantly undersampling, right? And all you're getting from any given pixel is the total amount of energy that pixel sees in that 10 microsecond period. So without any modulation, all pixels are seeing essentially the same amount of perturbation. They're seeing a perturbation if they have a susceptibility at a given frequency. They're all seeing pretty much the same perturbation. So when you take your statistics, how the detector teams would evaluate susceptibility, they're basically still seeing a uniform field, and the initial indication is we don't see a susceptibility. And going a little further into the weeds here, but you know, at unit level tests, we saw some susceptibilities that at frequencies that I was looking out for. In fact, it was I was pretty sure it was due to resonant cable lengths that were going to be different on the integrated ISIM. So I was predicting that those resonances, those susceptibilities were going to shift in frequency. And it turned out they were right in the range that I suspected that they would be. And little bit of a tangent here, but when I learned that, when the teams, called me over to the control room to show me the susceptibilities landing right in the frequency ranges where I thought they would. And I was practically jumping for joy. And Rob Houle said, "This is the first time I've ever seen anyone actually happy to see a susceptibility." So go figure, another first there. But anyway, back to the point, we were initially not seeing susceptibilities where I was pretty much certain that we should. Like, we went through the whole frequency range and didn't see any susceptibility, and just something's not right here. Well, it turned out that those new shiny signal generators, the way they were configured, the modulation was not applied internally, even though the front panel was saying your modulation's on. We're applying that 1 kilohertz, the 1 kilohertz pulse modulated signal, so that it should be on for 500 microseconds and off for 500 microseconds. So about 50 pixels should see the applied signal and 50 pixels would not. So you should see the striping pattern if the modulation signal was applied. Well, we weren't doing that because what we didn't grasp was that, or I think I don't remember if we'd actually paid for the option or not, but we didn't. The machines that we got did not have the modulation could not be applied internally. You had to run a cable from an external connector around to the front port to have the modulation actually take into effect. So it was telling you that the modulation was working. The signal was internal, but was internal to the unit. But you had to run a cable physically from the back panel to the front panel to actually apply it to your to the signal that you were applying to the EUT. So the signal we were applying was not modulated, and we learned this after about a day and a half of scans. And once we got that sorted, we repeated the scans, finished the test in that one additional day. We did have that setback, which was not fun. But I will say that when I went to management, I mean, I was the test lead, the test director, so I was the one who had to go to management. It was Jamie Dunn, was the ISIN manager at the time, and I had to throw myself at his mercy, saying, "Well, we screwed up here. I probably used the F word. It was Jamie, and I've known Jamie a long time, but we screwed up. We messed up. We erred here. We got to go back and repeat these scans." And as I was throwing myself at his mercy, he said, "John, slow down. You didn't damage anything. You didn't break anything. All you did was lose some time. All right. It's clear you guys know what happened. You know what you need to do. You guys are doing a great job. Get on with it and get on with the test." And that was it. That was the royal ass chewing that I was afraid of. So again, I tell that getting a little sentimental as I'm getting close to retirement, but that was definitely a pivotal moment in my career when I realized, if you're just up front with management, you tell them you screwed up, but you know what you need to do to fix it. What more can they do? They just say, "Okay, then get back to it and get on with the test." So definitely pass that along. The worst thing you can do is try to cover it up. Just admit that you screwed up, especially if you're the one that they need to fix it and make things right. Then they'll let you get back to it. Anyway, that's that war story. That was the ISIN test. Any questions or comments on any of that? I'm going to shift gears and talk about the spacecraft test. Anybody still there? Can I get an I am okay?
Here.
Still here.
All right. All right. So here was the spacecraft EMI test, the conducted portion, April 2017. There was a JWST spacecraft, clearly without payload integrated. So this was spacecraft only. Here's just an overhead view. Again, just showing where the antennas are. We had an Omni over here. This is the gimbaled antenna assembly. So this is the high gain antenna for K-band downlink, and the medium gain antenna MGA for S-band uplink and downlink. Here's just another view showing the S-band Omni. That has the cover is installed. Obviously, we took that off for radiated testing. The GAA is back here where you can't see it. So here, again, at spacecraft level, what we're concerned about are the launch limits only. Okay, so we have the command destruct band in the 420 to 480 megahertz range, and so being very specific about our victim allowed us to be very strategic and efficient with how we ran the test. So if we're only concerned about this frequency range, we decided to run this test with tuned dipoles, which were much easier and more efficient to put in place than the standard large double ridge guide horn antenna that would normally be used in that frequency range. Any of you know that large DRG horn is a big beast, and it would have been very cumbersome and really would not have fit where we needed it to fit without significant work. So we'll get to that here in a minute. Another factor was that we needed an RF tent for this test to reduce the ambient level in the high bay. It was an RF rich environment, less than 10 miles from LAX airport. Actually, according to Google Maps, as the crow flies, it's like right around 5 miles. An RF survey taken within a year before the test showed occasional levels 5 to 10 dB above the limit. So it wasn't surprising knowing we were in an RF rich environment. So we needed about 10 to 15 dB of attenuation to bring the ambient level to 6 dB below the limit, which was really the goal for being able to perform the test in a meaningful way. And we needed to minimize reflections around the dipole antennas inside the tent. So we placed RF tiles on the floor in front of the dipoles, and RF absorber walls were placed behind the dipoles. We also used the Roden Schwartz ESW. We got an I believe Northrop rendered an ESW-8 specifically for this test. I think I strongly recommended it. They didn't have one, and I strongly recommended that they get one. They weren't able to, or I guess they initially didn't feel strongly enough about it to buy one. Because a full up, an ESW-44 like we have is about $200,000. So they were able to rent this one. And again, it was kind of reluctantly because I forced the issue. By the end of the test campaign, they were like, "Oh, how soon could we get one?" I mean, once you use these ESW or any FFT machine, you don't want to go back. Anyway, so we're concerned about radiated fields or fields radiating in the direction of the launch vehicle. So, that's our 0.675 meters below the separation plane. So that, and in the test configuration, that's at where the spacecraft mounts to the test fixture here. I believe they called this the elephant stand. And so we put these dipole elements parallel to the floor for all measurements. So our horizontal and vertical polarizations, the elements were parallel to the floor. So it's just kind of relative to how they were pointing at the spacecraft. Right, so parallel to the spacecraft cavity or normal to the plane. And then just another consideration here is you had the two cavities, and just calling them cavities because there was not a panel. So plus and minus J2 had these panels in place, and so that you can see from the picture. I'll go back here. The plus and minus J2, those are panels, and there's equipment mounted to the other side of this. One plus minus J1, those are just cavities. There's no specific panel there, so this equipment is exposed. So we just decided that testing, testing here near the plus minus J2 panels was not very meaningful. Like that's providing at least some level of attenuation. The more important locations were to have the antennas in line with the plus minus J1 cavities. Where we were. Okay, so here are these dipoles. There's unfortunately not really a decent sense of scale here, but as I recall, the tip to tip was about a foot, not much more than that. So these were These are very small and certainly smaller than the DRG and much easier to put in place. Right, so this is showing what we call horizontal polarization, and this is vertical polarization, just rotated 90 degrees, but still parallel to the floor. And then the RF absorber walls behind it. We did some tests at Goddard showing that just surrounding this thing with ferrite tiles, even without it being completely surrounded, just putting it in a little cavity, just with ferrite tiles, significantly reduced the ambient levels that it was measuring. So that made a lot of difference. This is just another view here. And then this is a pretty cool view of, you can see the RF absorbers surrounding the spacecraft. And then here's the tent ready for assembly. We've been using tents like this for testing at Goddard. Maybe from the same manufacturer, I'm not entirely sure, but anyway, one goes in place, the other goes in place. So there's the test assembly. The tent is now fully assembled and ready to go. So the tent did its job. The minimum ambient level was about, or maximum ambient level was about 10 dB below the limit. So that's good. But except when anyone touched it. When anybody walked near, or especially if they touched the tent or come anywhere close to it, you would see what were clearly these ESD type events, and that would generate broadband emissions that would temporarily raise the level above the limit. This was clearly not, it was not caused by any specific transmitter. It wasn't a single frequency. And we would not have observed this as effectively with a traditional frequency swept receiver. So while the FFT machine was maybe not really necessary for this specific test, it really showed its worth here, because if we had been using a traditional frequency swept machine, we would have only seen any indication of this transient at the frequency where the sweep was at the time that the event happened, right? So you get what looks like a spike, which would look like some specific transmitter. And so it could lead you to think, oh, well, we have something happening at whatever, 423 megahertz. What is that? And it could lead you down this troubleshooting rabbit hole that would not be time well spent. You'd be chasing a non-problem. Being able to see the entire spectrum instantaneously, I mean, the only thing that realistically causes this sort of thing, that causes this kind of a broadband spectrum in the frequency domain, is a transient event. So when we saw the entire level come up very quickly and then come back down, we were pretty quickly able to come to the conclusion, especially when we could see, okay, that's happening when somebody is going near the tent. Like, okay, we're looking at ESD events here. So we just need to keep people away from the tent while we're trying to take sweeps. And so we had our attack dog services in place. I don't believe Ken is on. Ken hasn't been participating for a while, but Ken Jabor, in fact, back here, I'm pretty sure that's Ken right there. And so he was just standing guard while we were running our sweeps to just keep everyone away from the tent, and I think that's probably when we set up the perimeter here, because there's other stuff going on in the high bay, and we weren't able to get a high bay clear for this part of the test, so we just had to deal with it. But Ken was at least able to snarl at people if they got too close to the tent. So once we got that in place, we were able to complete the test, and then it was pretty benign. We had a few little peaks in the frequency range of interest, but they were all below the limit and passed, and we completed spacecraft RE in one day. So you should be noticing a pattern here. When you plan these tests well in advance, you should be able to complete each one of them in a day, and that's highly desirable because the setup and takedown is non-trivial. Like when you spill over into a second day, you generally had to dismantle some things, and it's not always trivial to just pick up right where you left off. Like you may have to set up a significant amount of stuff again. your mileage may vary, but anyway, just if you can complete these tests in a day, it's always highly desirable, and it's very doable when you plan them in advance. So radiant susceptibility. We performed this at spacecraft level only at the launch level tent poles. And so for whatever, I guess, because they defined it in dB microvolts, it's 145 dB microvolts per meter, which converts to 18 volts per meter. Generally, RS should be defined in volts per meter directly. Just it's another delineation where RS is defined in volts per meter and RE is in dB microvolts per meter. Clearly, they're the same, they're equivalent, but that's just another way of really differentiating the RE and RS limits and not getting them mixed up with each other. So we have these discrete frequency ranges, these discrete tent poles, and between 1 and just under 6 gigahertz. All right, so that's what we tested. And we were able to get full coverage with one antenna location. So we looked that we needed a 3-meter beam width to cover the full plus minus J1 cavities with a single antenna location. But again, this was highly desirable. We were still going to need, we needed more power than we could put through one of those log spirals. So we were going to be using this, the DRG, small DRG. So we're going to need to do 2 polarizations, but that's okay. Going with one antenna position still was made things much more efficient. So below 2.5 gigahertz, you can see the frequencies here are, there's a convenient frequency break at 2.5 gigahertz. I think that was an amplifier change. I think there was something that just landed nicely for us that we had to change amplifiers at 2.5 gigahertz anyway. So we could do these lower 2 tent poles with one amplifier and then switch to another amplifier for these upper 2. So below 2.5 gigahertz, well, looking at the beam width curve, the minimum 3 dB beam width was 55 degrees. So there we could achieve that if we put the antenna 3 meters away from the cavity. And above 2.5 gigahertz, 2.5 to 6, we didn't have to go all the way up here. Again, using this to our advantage, we were only concerned about those tent poles at up to 5.9 gigahertz. There, the worst case beam width is 33 degrees. So there, we could move the antenna back to a distance of 5 meters to get that 3 dB spot size. And so with the 200 watt amplifiers were sufficient to deliver the needed power. We needed 30 watts to get the desired field strength at 3 meters, 41 watts at 5 meters. So we had plenty of headroom there. And as I mentioned, there was that frequency break at 2.5 gigahertz for an amplifier change. And so there was no significant impact to move the antenna while changing amplifiers. We had to do that anyway. So the two different antenna locations was incidental. Right? It wasn't really a separate antenna position. You had to change amplifiers anyway. So a single. Let me rephrase that. Yes, it was a different antenna position, but it was minimal impact. I've said that a couple times. We had to change the amplifier anyway, and just moving the antenna back while changing the amplifier didn't really add much to the test time. So a single set of RS scans was required for each cavity, and again, we completed RS in 1 day. Well, another war story for you. So these Tweeta amplifiers, we use them on spacecraft, but they're also commonly used for RS testing. That's what Northrop used. These Tweeta amplifiers for driving the RS antennas are notorious sources of broadband noise. And that noise gets transmitted right out of the test antenna or the EUT. Now, generally, when you're applying your desired signal, that's significantly higher level than the broadband noise, so it's generally not a big concern, right? But in this case, we had the S-band on the antenna right in the field of view of our test antenna, and the noise level that was applied to the receiver, that Omni received and then carried to the receiver input was about 70 dB higher than the hardline S-band uplink signal, the test uplink signal we were applying from the RF test set, which was at about minus 110 dBm. So we lost lock on the uplink as soon as the tweeter was powered on, before we even applied a test signal, and that halted the test. And this was documentary footage of me in the control room. And I was gonna ask. I forgot that I put put Sunday on there. I was gonna ask if you had a guess on what day of the week this happened. Most people guess Friday afternoon. And no, this was a high profile test, and we were working weekends. It was a Sunday morning. So it's an RS test. So it's, when you're evaluating susceptibility, you've got the whole team, the whole army sitting on console. For an emissions test, you're generally dealing with a bit more of a skeleton crew. But here you had every subsystem sitting on console to evaluate data for susceptibility. So it was a big to do. There were several dozen people in the control room, and we were all set up, CDH go, power go, going around the room. Okay, we're go. Then my team flips on the tweeter, and we lost lock on our uplink signal, and now it's okay, John, what the fuck do we do now? Excuse me, what the heck do we do now? And it was a very intense, it's probably one of the more intense couple hours of my life, and certainly of my career. And once we actually got a handle, fortunately, the EMI lab technician who was running the equipment, the one who actually flipped the switch on the tweeter, immediately he said, "Oh yeah, these tweeters are notoriously noisy, and that's probably what we're seeing. The tweeter noise is just going out that antenna and blasting the Omni." And it's probably dwarfing out the uplink signal. The uplink was provided as a hardline signal, so we had direct control over what that level was. But the antennas were open to space and still receiving whatever they could pick up from the RF environment, and carrying that energy to the receiver input. Now, we did some, and this again, Ken Javor was out there supporting the test in person with us, and he was instrumental in turning around some calculations very quickly to determine, most importantly, we didn't damage the front end of the receiver. We had, I don't recall, but 20 some dB, maybe 30 dB of headroom in what the worst case signal could have been, that hit the receiver front end. It was 20, 30 dB below the damage threshold. So that was like first and foremost. Okay, we didn't break anything, and then it was also in that same set of calculations that we learned. Okay, we were applying a signal that was about 70 dB more than the applied uplink signal. So of course it's going to dwarf it out, and of course this is what's going to happen. Okay, so it went from it went from looking like this guy here. That's like the worst feeling ever, of like something really bad happens and you have no idea why. But within probably an hour, we got to having a pretty good handle on what happened, and the fact that we didn't damage anything. So, that's a testimony to the whole team working together. And I definitely was relying on the other people in the room to provide some of those inputs. But once we were able to kind of settle in and, okay, what are we going to do about this? We saw that maintaining lock on that S-band uplink signal was determined to be unnecessary for the test. It was an unnecessary success criterion for the test. Because on the launch pad, the uplink signal is neither critical nor at such a low level of minus 110 dBm. That uplink signal is only required after we separate from the launch vehicle. and that uplink signal will be much greater than minus 110 dBm. And those 18 volt per meter levels from at the launch site environment are no longer part of the electromagnetic environment. So this whole thing of maintaining lock on the S-band uplink signal was unnecessary and an unrealistic success criterion, but it was interpreted as being an important success criterion, certainly by Northrop Grumman. And this is where we had everyone was gathered in a room. Here again, it's part of the context here is this being a Sunday, people are giving up. I should say, not really giving up. It's part of their, it was our job to be there on the weekend. It was our job to be there on a Sunday doing this test. But it's a weekend. It's a high profile and high stakes test. And if we had to punt that day, if we said, okay, we can't complete the test today, we have to, go into FRB mode or do any of this other stuff and get approvals up the food chain before we can proceed, it probably would have been a several day hit. Getting everybody assembled the very next day, maybe, but it wasn't a guarantee. I mean, it might have been a several day hit to the test campaign if we had to do that. And so here's one going beyond the technical. I'm passing this along as going beyond technical inputs to a test like this. I specifically negotiated decision-making authority on behalf of Goddard and NASA and the U.S. government in advance in writing before this test. I went to my management and had this conversation. I didn't know this specific thing was going to happen, but I said, in just about every test campaign, there's always some moment like this that requires somebody in authority on behalf of NASA to make the decision. And I asked my management to give that to me and put it in writing to Northrop Grumman management so that there would be no fuzz on it if something like this happened, that I would have the authority to make the decision to keep the test moving. If once we determined that the spacecraft was safe and that it was safe to proceed. And they did not hesitate in doing that, because they said, we're going to be looking to you to make those decisions anyway. So I said, well, then let's please make it formal so that we don't have this churn and spinning around or whatever euphemism you like, but the churn time that can happen when you have an event like this happen during a test campaign where it's nobody wants to move until there's some formal edict from someone in authority. I said, please just give me that authority so that we can keep the test moving if something like this happens. And I said, rest assured, if something is that I feel is above my pay grade or that I will let you know. And also rest assured that after we made the decision to keep moving with this test, I was on the phone with my management to tell them exactly what happened. But again, I passed this along that, if you can do this in advance and get it in writing, if you're willing to be, take this on, and you should be if you're the test director, that it can really save a tremendous amount of hassle if you have something undesirable like this happen during a test campaign. If there's damage or even any concern of stress or anything like that, that's a different ball of wax, and you definitely call management and get them involved right away. But here, once we actually understood what happened, we had an unrealistic success criterion that the contractor they were interpreting as a requirement, and they needed some relief from it to agree to remove it as a success criterion so that we could get on with the test while everyone was assembled there. And we lost maybe 2 hours, but at this point it was still about noon, and we knew we were going to be there all day and into the evening anyway. I said, if we're all agreed that this is what needs to happen, we can get on with the test and still finish this today if everybody's on board with it. And I went around the room, or I just asked, does anybody have any objection to this? Because if you're looking for NASA approval to remove this as a success criterion, I'm here to make that decision and let's get on with it. And nobody objected. And they were all very happy that, we made that decision and I got everyone's, input. I said, please speak up if there's something I'm missing, but the RF guys were very happy to get on with it and happy to have that disposition that yes, we could remove this as a success criterion. It probably required a waiver after the fact, but that could catch up. We had all the people right there ready to finish the test, and that was the important thing, at least in my mind. There was no reason to put this off for another 3 or 4 days for something that we fully understood and everyone agreed was the right course of action. That was that war story. And so this was one of the key documents we looked up at the time that said we don't need to get a command to the spacecraft. This is the Ariane User's Manual, right? We're not looking to get a command to the spacecraft until more than 20 seconds after separation from the launch vehicle. So right there was our justification. This wasn't something that we were just making up. We're like, okay, it was already an unrealistic and unnecessary success criterion, and this gave us our justification to remove it so that we could get on with things and test the rest of the spacecraft. And then once we got on with it, then that was our exciting bit for the day. The rest of it was wonderfully boring. No susceptibilities were observed, and we passed. Again, RS completed in 1 day, even with the tweet and noise setback. And I can't say enough, negotiating that decision-making authority in advance was instrumental. I mean, how should I say? It's not for the faint of heart. Notice that the picture of the screen. It was an absolutely horrific couple of hours. It's not for the faint of heart to put yourself in that position of being that decision-making authority, but if you are the test director, that basically is what that means. People are looking to you to make that decision. So just make it clear up front. But also, get the input from all the people there. We had all the right people there in the room to help make this decision. And, and once I was convinced that that was the case, then, all right, this is the right thing to do. And then I had people just, okay, get on with the test. I'm going to go make a couple of phone calls to management to let them know what happened. But, this was one case where I can say, like before, there was the case of throwing myself at Jamie Dunn's mercy. But here, I just was telling management what happened and what we did about it and that we're getting on with the test. And I didn't catch any flack for that one. They were all like, great, you took care of business and that's great. That's exactly what we would have hoped for. So if it had gotten to a point where where I wasn't comfortable making the decision on my own, I would have called management and said, okay, I need a little bit more muscle here. But like I say, I definitely encourage you, if you're in charge of a test like this, make sure you get this kind of decision-making authority in advance and in writing, because it can really save your bacon. All right, last thing I want to cover here is RF self-compatibility. So it's RF communication subsystem is a possible victim. So the MIL standard 464 provides guidance that to verify that you have 6 dB margin of your RF uplinks. We'll talk a little bit more about that. It's kind of the main thing I'll be talking about. But so method 1 that is recommended by our MIL standard 464 is that you disconnect the coaxial cable from the uplink antenna at the uplink receiver's input if accessible, and then connect it to a test receiver or spectrum analyzer sweeping the frequency band of the uplink receiver. Now, we don't generally do that on Goddard missions. I don't believe I've ever seen it done, but I think it's more commonly done on maybe some DoD missions. But and then you put the spacecraft through a mission sequence profile, and then you directly measure what the antenna sees. So you can just look directly at what the antenna is seeing and make some assessment. Is is it okay or not? And then you want to determine that the measured noise level or RF background really in the receiver band is at least 6 dB below the maximum permissible noise level that will allow the minimum signal specified by the link budget to meet the signal to noise ratio requirement. So this is better suited to platforms with a large number of communication channels, where you can look at a wide range of frequencies at once. So method 2, which is more typical for what we do on Goddard platforms, you apply a signal that is 6 dB below the minimum level specified by the link budget, put the spacecraft or observatory through a typical mission sequence, and if you maintain lock on the uplink signal throughout that, then you've demonstrated that you've met the 6 dB margin requirement. Now it works best with a limited number of communication channels. JWST had one. We had that S-band uplink channel, and that was it. So that was all we had to monitor. So here's the verbiage from Mil Standard 464. Again, this is the sort of thing you're going to get from Mil Standard 464. It doesn't spell out all that stuff that I just said. It says safety critical and mission critical system functions shall have a margin of at least 6 dB. Compliance shall be verified by test analysis or a combination thereof. Well, the uplink signal counts as a mission critical function. So the way we interpret that is if you look at the minimum uplink signal level that's defined by the link budget, and that's going to basically take into account what's the minimum signal to noise ratio, right, for your receiver performance, and so you want that to have 6 dB margin with respect to the spacecraft RF background, right? Or so whatever the minimum signal noise ratio that your receiver has, and whatever that minimum uplink signal that the link budget requires, you want there to be 6 dB margin between the spacecraft RF background and that base of the signal to noise ratio, the minimum signal noise ratio that you want. So the first method, that I talked about that comes right from Mil Standard 464C is you disconnect the cable on the spacecraft going to the antenna, or go from the antenna to the receiver, and then you run a cable to a test receiver and then measure what's there. Okay, but again, we generally don't do this on Goddard platforms. It's a really excellent way to do it if you have it, if there's a test port on the spacecraft, like ideal if you don't have to actually break a connection, if there's just like a coupler on the spacecraft. And it's done. I've just never done it on any project I've supported. So this alternate approach is like on JWST, again, that's our case study here. We had a single S-band uplink channel and frequency, so there's no wide band to test. So we apply signal in the center of the S-band uplink range that's 6 dB below the minimum level specified by the link budget. And we demonstrated that we maintained lock under the worst case conditions, putting the spacecraft through its paces, generating maximum RF emissions. And, whatever time we specified that we run, I don't know, 10, 20 minutes, whatever it was. And we maintained lock. And so thereby we demonstrated our 6 dB margin and we met the requirement. Now on RST, most recently we employed a somewhat different approach. It also has a single S-band uplink channel. This was just a couple weeks ago, actually. So we measured the command, or the RF team measured the command threshold, which is more important one, and carrier threshold at unit level. Carrier threshold is just kind of additional data. You're pushing the noise floor of the receiver there, so you're going to get a bit of variation on that level. Command threshold, is I think about 10 dB above the noise floor. It's just a more reliable measurement, and it's the more important one. You want to make sure you actually are getting commands in. So that was verified at unit level, at component level, that it was 6 dB below the minimum level specified by the link budget. And that wording is kind of clunky, but you get the idea that we had 6 dB of margin with respect to the link budget. Then measured it again at integrated spacecraft and then also at SCIPA, spacecraft plus integrated payload assembly levels. And man, these charts are more sloppy than I like to admit. But okay, we're almost done here, so stick with me for just another few minutes. So we measured this at spacecraft and SCIPA levels. And so first with minimal equipment powered, basically just, with the bare bones equipment on the spacecraft powered. And so we verified in-family performance at the unit level, so within about a dB. Then turned the rest of the spacecraft on and verified, I believe it was less than a 1 dB increase, but it was still, in family with what we saw with the minimal power configuration, and it was still within the 6 dB margin level. So we demonstrated the 6 dB margin that way, just verifying in family performance between the full spacecraft powered configuration and the minimal powered configuration. So it's a slightly different way of verifying it, but you get the same result. You demonstrate the 6 dB margin and everything is good. So, okay, so with the RF communication system as a possible culprit, that's pretty straightforward. You're basically just running a CPT, right? You put the RF comm system in its most emissive on-orbit configuration, and then you run the non-RF equipment. You put it through its paces, the typical mission sequence. And it's generally some sort of CPT, comprehensive performance test, which all the equipment is put through its paces with the RF transmitters operating. And then if all of the non-RF equipment operates within spec, then you've demonstrated compatibility and you're done. And then non-RF self-compatibility is again basically just a CPT. You're running all your equipment through a normal mission sequence. It does provide an opportunity to determine if any particular component is interfering with any other components. So you can structure your CPT to address items of concern. If you're particularly concerned about one particular noise-making thing that's close to some other sensitive thing, you structure your CPT to specifically run that noise-making thing, and then you're specifically focused on the sensitive device during that time. Do we see any indication of any interference there? So it's basically just your CPT, just plan it accordingly. And here is the summary. So testing at integrated system level is inherently more complex and expensive than testing at the unit or subsystem level. You have your INT marching army, with associated schedule and cost implications, right? You've just got coordination amongst lots of people. So you start planning these tests well in advance. So clearly understood and defined success criteria can facilitate efficient system level test programs. Do your RE testing only in receiver notches. There's no need to test DC to daylight at system level. And RS testing only at specific transmitter tent poles. And use strategic antenna positions for both RE and especially RS. RS is where the scans are inherently longer, so you really want to be very strategic about your antenna positions for RS. And structure your self-compatibility tests with very well-defined success criteria. And with proper planning, each one of these tests can be completed in one day. And we've got lots of experience to back that up. And that's what I have. Anybody have any questions or comments?
So when you've got a GPS receiver, we're dealing with that and the capability of making sure that notch is not compromised by any, and I'll call it workmanship issues, when they're making the spacecraft. We have come up with, we're going to use the GPS antenna to do that test for RE at the system level. That has to be assessed for each spacecraft, what kind of testing needs to be done for your receivers to ensure that you've got an adequate notch, or whether you're going to use an external horn for doing that test, right?
Well, if you're using the GPS receiver itself to evaluate whether you've got emissions in that notch, I call that a self-compatibility test. You know,
The
as
problem
opposed to
is if you have spurs in the frequency band that are basically deteriorating the receiver's capability to receive, that might not be detectable by just using the GPS receiver in a lab and in a high bay environment.
you're asking for a
That's,
friend, right?
well, I'm saying that you got to
I'm,
consider those kind of things at the
I'm,
system
I'm
level test.
full disclosure, Mike and I have been discussing this very thing on a certain nameless project we're both supporting. But I mean, like we've been discussing, or at least, you know, our friends on this nameless program are discussing. I mean, if you are sufficiently concerned that you want to set up an external measurement antenna in somewhere in the vicinity of the GPS antenna,
Yeah.
you know, and make an external measurement, then that's an actual radiated emissions measurement. Right. I mean, you're setting up an external antenna, and if you have sufficient concerns that you want to see some granularity in what's happening in that receiver band, then okay, that's a radiated emissions measurement. That's not a self-compatibility measurement. And if you're using the GPS antenna directly going through the GPS receiver on the spacecraft, and using that to assess you know, any particular susceptibility, that's by definition a self-compatibility test. So, I mean, it's kind of a nomenclature thing, but I think it's an important distinction. Your ultimate figure of merit, to my mind, is the self-compatibility test. Like, ultimately, you want everything on the platform to be mutually compatible.
Understood.
So your ultimate the ultimate verification is self-compatibility. Everything you do before that is risk mitigation. You know,
But if
you
you're
measure radiated emissions at unit level to flag any potential that you might have some emissions, you know, in that receiver band, so that you can do something about it at unit level and fix it if it's bad enough, right? But the
right,
ultimate figure of merit is, you know, when you have a self-compatible platform. So
but
so
in that
that's really that. Go ahead.
in that self-compatibility test, you generally won't have a GPS transmitter simulator for all the GPS satellite positions and varying signal levels from them, right? Especially at GEO. So that's where I wanted to make sure we understood. Sometimes you got to consider the self-compatibility test really isn't sufficient to say whether or not there's a problem with a particular receiver.
And that gets into the nuances of each specific
Yeah.
receiver, right? I think generally the self-compatibility test for S-band receivers has been fine. I mean, I think that's been
Yep.
an effective check. And that's, you know, that's where the pencil sharpening comes in, right? You know, all of this
Yes.
is kind of, you know, my going in recommendations, but you know, if you have a situation where I forget, I'm forgetting the nuances, but I know we've had the conversations that the GPS receivers, you know, for the reasons you're saying, don't seem to offer that kind of granularity, that, and you might miss something from just a straight up self-compatibility test.
Yep.
Then okay, that may provide grounds for doing an additional RE test at platform level to see what else is coming off of the platform that might land in those receiver bands. And
Okay. Separate topic. You touched on it, but there's keep out when you're doing radiated susceptibility type testing. There's keep out frequencies that you have to establish up front for the particular receivers on a satellite, right? And so you said that when you got that broadband noise out of the tweeter, you had to look at what levels got into that receiver, I'm sure, right?
yeah, that was part of that 2 hours of terror.
Yeah.
What were the levels that the receiver saw? And I mean that the tweeter, that's just a test amplifier. I mean, it there's no notch filtering in that. That's just okay. Yeah. It will give you I mean the intentional level, whatever the power level it takes to give you your 2 volts per meter or 10 or 20 volts per meter level. That's much higher than that level of broadband noise. So generally the noise that's put out by the tweeter is not really a big concern. The main issue here was that we had that test antenna pointing directly at a receive antenna, which is not generally something we do. I mean, certainly when you're testing a non-RF component at component level, that's just not something that you ever even think about. Right? You don't have an antenna that's going to be particularly sensitive to those levels of broadband noise, and the main, the business end of the test is the main level that you're applying that's significantly higher. The swept ideally swept sinusoid level. But it was the fact that we had a receive antenna right in the field of view, and I mean,
Yeah.
I'll just freely admit here. I mean, we had lots of smart people playing this test, and all of us missed that.
Wow. Yeah.
Like once we like put all the puzzle pieces together, and we realized what we had just done. Definitely slapping my forehead. It's like I really can't believe we just did that.
Oh.
So don't try that at home, kids. Don't point your RS test antenna directly at a receive antenna on the platform. If you learn nothing else from today's session, please take that with you.
And the last thing was for the radiated susceptibility, get buy-in from somebody that knows something about range safety at the launch site, so that when they review what you've tested, they can say, yeah, we agree with what you did, and there wasn't insufficient testing for range safety or insufficient analysis done for them, because that can be really a long process if something comes up right before launch and you've already shipped the satellite.
Yeah, well, that again, using one of my least favorite words in the English language, should, but that sort of thing should happen in the requirements definition phase. I mean, the range safety people are the ones who are supposed to be defining those launch RS limits. And now
But things
we
change.
What's that?
But things change.
Yeah, and on RST even before, I think it was the spacecraft level test last October. I think Nick, are you still on? Yeah, Nick was spearheading that test, and I think he got a surprise within a couple weeks before the test. I think the launch site, launch vehicle provider said, "Oh yeah, we've got another notch we need, or a tent pole we need you to test, or maybe the frequency shifted or something." It turned out not to be a big deal. I mean, I think even if it was an additional tent pole beyond the ones we were already testing, it was in the noise, as it were, how much additional time it took. And we didn't see any susceptibilities, but it was kind of one of these things like, couldn't you have told us this maybe earlier than this. You know?
Yeah.
But yes, it's what I call a fecal occurrence, right? You know, but you can do the translation if, you know, to your heart's content. But
The
yeah, I
transcript's
mean,
doing it
you
for
find
us.
you find out these changes of direction not too long before the test, you know, and you try to plan the heck out of these tests, and
Yeah.
you know, eventually these surprises come up, but you know, you roll with it and you keep moving. But yes, those launch site limits, both emission, radiated emissions and susceptibility, those are supposed to be coming directly from the launch site provider. You know, that they are supposed to be, you know, and that it definitely should be getting them involved early on as you're, you know, writing and publishing those requirements. That's where those are supposed to be coming from. Now, a lot of times we're writing these requirements early on before we've actually selected a launch vehicle. And, you know, if you've got somebody writing the requirements who's done their homework, and they'll pull the worst case limits from the different providers' documentation and say, okay, here's our envelope, you know, and okay, that's fine, and we've done that sort of thing. But once you've actually down selected to your specific provider, and you know what subset of those limits that you need to test to, then definitely update the documentation to show what's really necessary, because you could have some fairly stringent limits in there from a provider that you're not using, and it's completely unnecessary and counterproductive to test the limits that you don't need.
Yep.
So.
Okay, thanks.
Yep. Anybody else have any questions or thoughts? Okay, well, thank you all for participating and sticking around for 15 minutes past the 2-hour mark. I thought this was going to be a shorter one, but hey, I stopped saying that out loud, at least when I get started. So thanks everyone. Have a good day and a good week.
Thanks, John.
Thank you.
Cheers, John.